Welcome to today's webinar. The topic today is most frequently asked questions answered by Dlubal support team. That's our regular webinar about questions that our customer asked in the last time, or customers ask for features and we can now present such features that are wished in the past. My name is Andreas Hörold. I'm responsible for marketing and PR, for example, for the German and English webinars. I will be the presenter today and I will present the first part of the webinar. The second part of the webinar will be presented by my colleague Stefan Hoffmann, who is the head of customer support. And we will answer your questions when the other colleague is presenting. How you can ask questions. I switch off my camera that you can see the full screen. You can press that button with the question mark, then enter your question here in that field, press send, and we will receive your question. And we will answer you. Okay, then we start in the program RFEM 6, and the first question is, how can I exclude objects from the design of individual combinations? The steel design is already done, but in the second step, we would like to exclude these set of members, these two, this one and this one, from a design situation. I show you the three design situations, and imagine we would like to exclude this set of members from the design situation 3. How to do that? There is a button here, objects to exclude. I can increase the table a little bit. Then I scroll down and we enter here excluded member sets. I select the 2 member sets. Okay. So, and I copy that in the next field with the key F8. So can you do that easily for more than 1 copies? That's quite easy. Okay, now, we can now run the steel design. But to show that in detail, these combinations are not used for the design of the set of members, I show you another new feature. So I go to steel design and with a right click, left in the table, navigator data, the mouse is here, right click, settings. And then I can display results by design situation. This feature is available also for timber design, concrete design, and so on. So I press the button, okay, and then I run the steel design again. So, and now we select design ratios by member set. At the bottom. So, and now you can see design situation 1, member set number 1. I scroll down, member set number 2. Then design situation number 2, member set 1 and 2. But design situation 3 is missing. You can use that also for larger models or when you want to exclude some members or surfaces from the design, just use this nice feature. Okay, then we turn to the next model and the next question. The next question is, how can I create a pre-deformed FE mesh like I used in RF-IMP? RF-IMP was the add-on in RFEM 5. And now it's also possible to create a pre-deformed FE mesh, e.g. for eigen value or mode shape. And we would like to do that in this example. That's a member. It consists of surfaces. I created a member HE, also with a cross section HEB 300, and created surfaces from this cross section. So, and we can show the results of the design loads, the deformation, or the normal deformation. Yeah, but we would like to create mode shapes. So how to do that? At first I activate left above. I go in the base data, then add-ons, and I activate the structure stability. Press OK. So, and now I go to edit above here, edit active load case. I turn to the dialog, load case and combinations. And for this load case, I activate the calculate critical load. The program should calculate the eigenvalues. So I open the edit button, I press the edit button. We would like to calculate the 4 lowest eigenvalues. Okay, I can press calculate. And now the stability analysis is running. First this static calculation or static analysis and the stability analysis. And at the bottom in the table, I activate the stability analysis. And now you can see, the 4 eigenvalues. So eigenvalue number 1, eigenvalue number 2, 3, 4. And we would like to use that mode shape for imperfection, to create an imperfection from it. So we turn left at the bottom to change the navigator data. And you can see here the imperfections. And I create a new imperfection case by right click and press new imperfection case. So, and I select imperfection type buckling mode. I can choose between load case and load combination. We will do that for our load case number 1. I turn to buckling mode and selected is load case number 1. We have got only one load case. We can select the buckling mode here, number 1. So, and then we use for scaling direction spatial. So I enter imperfection magnitude. We don't do a GMNEA analysis here. We showed that in detail in a webinar. Just go on our homepage, the webinars, and enter in the search buckling, and you will find the webinar when you would like to do a GMNEA analysis. Okay, assignment. Okay, that will be done later automatically. So now that is done, we have to go to in the navigator data. I select the load case to turn in the dialog load case and combinations. And now I create 2 load combinations. The first one left at the bottom, create new. I call it without IMP. Without IMP. So then I copy that one. So and rename it with imperfection. And I select consider imperfection, our imperfection number 1. And now we can compare the two combinations. I go to assignment. I have to assign the load case number 1. Okay, and now I can calculate all. So when the calculation is finished, we compare the two combinations. That is without imperfection, and now I turn to with imperfection. And you can see the buckling mode is considered in this combination. Okay, that was all for this question. So that's the next model, and the next question is, can I automatically consider the stiffnesses of steel joints in the global RFEM model? Yes, you can do that. I did it previously. We showed that function also in the webinar last week, but there were several questions to show that more in detail and compare the results. That's why I showed it on another example. You can see there are in the upper frame there are connections or steel joints created. Frame joint, this one, the first joint, and column-based joint. Okay, and you can see there are already member hinges created, but how does the program create such member hinges? I double click on such a steel joint. In the first step, you have to consider initial stiffness joint structure interaction. We go to the edit button. And this button must be selected. Generate hinges in the global model, and then with a stiffness calculation, the program generates automatically the hinges in the global model. Where are another default setting without that check, but we consider the initial stiffness, or we would like to do this joint structure interaction. Okay. Also for the first joint, so I go back to the frame joint, and under members, you need to select the stiffness analysis type, what you would like to consider. In that case, MY. So, and also for the first joint, MY on that place. So, and then we can select such a member hinge that was automatically created. Or better, just a moment. In the next step, you have to run the steel joint design. That's already done in our example. So, and I select the stiffness analysis, and you can see for the frame joint and for the first joint, the rotational stiffnesses. And that stiffnesses will be transferred automatically then in the member hinge. So let's compare that. So I select the member hinge, I decrease it a little bit, the window. So, and then let's compare the values. So, and you can see the spring, and yeah, this is this value. The rotational stiffness is, the output is here, meganewton meter per rad, and here kilonewton meter per rad. But it's the same value, and this one is this one, and it was automatically transferred to RFEM. So now let's compare the results. So in the lower frame, there's no rotational stiffness considered, and now we compare the results for no, I have to select left above static analysis. Then the deformation, you can see the deformation with considering the rotational stiffness or the member hinges is much higher. And when I select members and the internal forces, you can also see My is increased in the middle here. I can show that also in a better overview in the PowerPoint slide. You can see where the deformation, the internal forces, My, are higher in the middle of the horizontal beam, 2.6%, a little bit lower, 1.3% in the frame joint. But the deformation is much higher in the middle when you consider the rotational stiffness of the steel joints. And you can see it's necessary to consider such member hinges from steel joints, and RFEM does it at the moment or now automatically. Okay, that should be the first part of the presentation. I hand over to Stefan. Stefan, it's your turn.
Thank you, Andreas. I will continue with the next topic. The next question we want to take care of is how can I adjust the stiffness of objects? So as known from RFEM 5, maybe you know that there are already various options to do that. And for RFEM 6, everything is more or less controlled mainly with the structure modifications you can assign. So let's have a look into it. You can modify the stiffness of various objects. So this part will mainly consider materials, members, and surfaces. But as you can see in a structure modification, you can also modify the stiffness of materials and sections with a factor, for example. You can assign some for members and surfaces. I will come back later on that. You can also, if defined, modificate the stiffness of some other objects, as you can see, notice supports and so on. You could even deactivate objects fully if you want, for example, consider that one beam is not existent just for testing purposes or to analyze how the structure will interact. And you can as well also to take care and ignore nonlinearities just to check what their outcome may be on the results or not. But at first, we want to step in and check what we can assign for members and surfaces. So as you can see, once you activate members, there's a next tab where I did already define a member modification for one of my two members in my example. And you can also edit this stuff. So I defined a bending stiffness of 0.5, so it's half of the bending stiffness into the main axis. You can also choose between different modification types. So as you can see, you could assign a global factor for all stiffnesses. You can either choose for some other standard specified topic, so you can see what is then included in there if you need to choose them. But we want first have a look just with a simple example and see what will happen if we reduce the bending stiffness by 2, so 0.5. And we can also assign it for surfaces. So as you can see, I have assigned it to structure modification 1 for one surface, and I adjusted the bending and torsional stiffness to 0.5, so half of the value. You can also choose between all other categories which are shown in here. So if you want to adjust the multiplication factors for some stiffness matrix element, you can see how our matrices are meant to be. You can assign a factor in here, but we just want in our simple example show on how to use it and what the outcome may be. And second modification, we want to consider a factor for materials. So the best thing would be, in order to see the outcome in one file, to define doubled materials. And I just simply set the E modulus to half of the existing one. So this factor will also divide it by 2. So we should see some bigger deflection. I simply assign the structural dead load to my two members and surfaces. So the bottom part is without any modification and the top part is with modification. So let's run the analysis. And the outcome should be as maybe expected. Once we have the results, we can see that with the same loading, half of the bending stiffness will give us most likely doubled of deflection. So this was considered with a member and a surface modification. We can also globally do that for materials. So the bottom objects have the normal material and the top objects have the modified materials, and the outcome is, of course, nearly the same. So if we reduce the stiffness, the system and the objects will, of course, interact in a different way. It's not only limited to choose the modifications in a load case. If you're using the known design situations and the combination wizard, the best and easiest way just to modify the stiffness for every combination is to assign the consider structure modification also to the combination wizard, and then all your expected created combinations, load combinations, will include this modification. So you can adjust your total model with this. All right, so let's go to the next example. The second question I would like to present to you is how can I analyze a pile? So it's a member type which was just introduced into our program some versions ago. Let's step first into the activated add-ons, what we choose. So for the soil, we have a nonlinear material behavior. We use the construction stages analysis for the soil to be settled as an initial state, so-called. And we, of course, need a geotechnical analysis in order to define the member type of the pile. We have a simple example in here. So we have one pile, 5 meter length, 90 centimeters diameter, and we define our soil massive. First of all, we start in our example with the material. So it's a modified hardening soil material with defined values. Then we define a borehole. So it's a simple structure just to show you how you can use the member type. So it's just one material, 10 meters depth. And we assign this borehole to our soil massive. So this will create with the size we enter our solid. So you can see the solid is created. And then we start by adding the member. So it's a certain member type. You can see the pile. And if you choose for the pile, you have to see that there is a new tab where you can assign a pile resistance type. So in our case, currently you can choose between trapezoidal or varying, and you can enter your values of your pile, what you expect how it will interact with the soil. Once you have done that, I just want to step into our loads. So we have the dead load of, let's step into the load case, accept the soil solids. Then we have the activate self-weight for the soil solid, and we have a 1 kilonewton load, which will be multiplied later on in our file. In order to have a good calculation, it is very important that you can as well hit in the mesh settings independent mesh. So you will not have a fine mesh due to the members, but the mesh will of course interact. You can also as well decide if you want to have a certain target length of your finite elements. And it's also mandatory to check what integrated objects are in the solid and how they are going to be used. So you can assign line 13, which is the line of our member pile, to be independent mesh integrated. If you have done that, we have in our example now 3 construction stages. So there's an initial phase where we have a linear elastic calculation guided by the just explained structure modification. So it's a linear analysis of our nonlinear material model. This is just to prevent from numerical problems. That's normally used in this case. The second construction stage is meant to have then the nonlinear soil acting. So it's like settling nonlinear. And last but not least, the next stuff is introducing the pile into the soil and adding a 300 kilonewton, 30 tons load. So we can run it. So if we run construction stage 5, of course, it will start with the first stage where the soil is most likely just assigning the dead load. And then it's the nonlinear behavior of the soil in the next stage. And last but not least, the last construction stage with the load on the pile. Further analysis on the pile or information will be given as well, of course, in the next geotechnical webinar. So once we have results, we can evaluate them. And I think the best way is to use, for example, a clipping plane. So you can just use our planes, what we introduced. You can simply activate it, and then you can see, for example, the deformation. You can also slide it if you want to, if it's necessary for you. And you can, of course, as well display some results of the soil, so the solid stresses in order to evaluate them, or if it's necessary for you, you can also disable the clipping plane and simply check for the internal forces. For example, the normal force in the member, which is of course then given into the pile due to the interaction of the defined springs and the interaction so-called with the soil. All right, so let's step into the last topic as of today. How can I use the combinatorics for road bridges? So it was just introduced some versions ago. In order to activate this combination, you have to check in the Standards 1 tab, the standard group. So we introduced the Eurocode 0 road bridges with 2 annexes. And I have already defined my loads on my 2 strips bridge, so the left lane and the right lane. In this webinar, the topic is not about defining the loads, it's just about the combinations. So we simply just quickly explain the loads. It's the dead load, then the mainly loaded line 1, mainly loaded line 2, some pedestrian and cycle loads, some acceleration and braking loads, and then there is a tandem load model going over our bridge. This can also be created, of course, with our load wizard in RFEM 6. And then we have some temperature loads. In order to correctly combine the loads, we have to assign certain action categories. So you can see, of course, that there is the normal load model categories and also some construction loads and so on, depending on what you would like to analyze. And the main effort you can, of course, think of is that if you assign it, for example, to group 1A, don't miss that there will then be an additional tab where you can choose the type of the load. So our UDL loads will get assigned to the UDL. The pedestrian loads also added to group 1A will be assigned to pedestrian and cycle track. Our tandem loads will be assigned to TS loads, and of course accelerating and braking is also added in the group 2 with additional settings to braking and acceleration forces. The next thing is, if you have multiple temperature loads, you can think that they will act simultaneously, alternatively, or differently. In our case, it's alternatively. And then you can step on and choose in the base, of course, that we want to use result combinations, and it will then, of course, create us our result combinations, which we can later on evaluate. All right, so once we, of course, have defined all our loads, we can simply run the analysis and check for our results. We will not evaluate every result combination, but just one. So it's simply meant to show you that, of course, the loads will then be taken into account, and you can use the combinations for road bridges.
Thank you, Stefan, for your presentation. Just an additional hint from my side. You can book our online courses, for example, the RFEM 6 Masterclass course, that's for beginners, or the Eurocode 2 course for the reinforced concrete design, Eurocode 3 steel design. For more information, you can press the links at the bottom, or you can scan the QR codes. The courses takes about or between 2 and 3 hours. You can stop the course anytime and continue when you have time again. Just as I said, click on that links for more information. Okay, that should be also all from my side. Thank you for your attention. Thanks to Stefan for your presentation and for answering the questions when I presented. I wish all a nice rest of the day. Bye-bye.